It's a pleasure to speak at the Data Science Institute. And today I'm going to try to motivate a recent approach we've taken to understanding how to learn from the data for a class of stochastic epidemic models. And so in particular, what we want to do is kind of connect a lot of the rich modeling traditions from mathematical biology, for instance, and other disciplines to sort of a classical theory of rigorous inference from statistics. As we'll see, a lot of times the sort of choices we make during either modeling or inference for these methods can rely on a series of approximations because of the challenges that I will motivate here. And because of that, we often can not know what kind of biases might arise in our inference. So what I want to talk about is we're still going to focus on a relatively simple class of models, but motivate a perspective that we're now building upon the foundation from that enables us to do exact inference for all sorts of challenging missing data settings. All right. As an introduction, epidemic models, I'll focus on understanding the spread of disease, as the name suggests. But in many disciplines, we want to use such models to maybe understand the spread of other things, such as information, ideas, or behavior among a group of people or network. And oftentimes, we want these models to mechanistically reflect what we know about how this contagion spreads. We'd like to account for some structure and rates of contacts in the population, and I'll say a little bit more about that later because a lot of the sort of popular models do not account for this kind of heterogeneity. And then finally, because I'm a statistician, we're also biased towards stochastic models. So we want to be able to allow for randomness, and we'll be doing this in a continuous time setting that's sort of the most flexible for how these processes can evolve. So our focus will be on modeling and inference today. And my main goal is to simply motivate this challenging problem. So why is it interesting to try to derive inference methods for this setting? And why is that hard, even in the simplest, most prevalent models that people talk about? We'll discuss some of our contributions to overcome these challenges in such models, and then motivate how doing so will allow us to extend these models to be more flexible and realistic for many modern data settings. So just to begin with, about 100 years ago, the kind of beginning of this mathematical tradition, Kermick and McKendrick wrote this sort of landmark paper in 1927 introducing one of the most popular stochastic compartmental models used today. In fact, in their work, they had not introduced the probabilistic parts of the model yet, but the SIR model, or susceptible infectious remove model, tries to describe the process of an infection moving between groups in a population by disease status. So in this case, susceptible people will become infectious, moving to the I compartment, which will then become recovered or removed, moving to the R compartment. So if you work on epidemic models or read about epidemic models, you've probably come across this. And in this early work, they actually extended this to much more general settings, but it was purely deterministic. So these dynamics, how these populations flow between compartments, were described by rather simple sets of ordinary differential equations, such as this presented here. In particular, we already see that there's interaction from this slide between the susceptible and infected populations, such as in this term highlighted in red. And so this interaction introduces nonlinear effects that, despite the simplicity of this model, will complicate analysis and statistical inference. Now, there's also a stochastic version of this SIR process. And in this model, we simply replace those differential equations, kind of these rates of change described by derivatives, instead by the instantaneous probabilities of such events happening. So this should look very similar. We have a similar term here that describes the interaction between susceptibles and infecteds, multiplied by some rate of transmission, which is denoted by beta. And we also have the recovery rate, denoted by gamma, that is sort of multiplied by the same infectious population as these infected people are recovering independently. But on the left-hand side, we have probabilities of an event occurring in a small interval of time, rather than instantaneous rates of change denoted by derivatives. Okay? So we've basically replaced the deterministic version with instantaneous jump rates of a Markov jump process for now. So formally, this is a subclass of continuous time Markov chains, which is a really nicely well-studied class of objects in statistics and many other fields. One thing I want to mention is that implicitly here, both in the one I introduced in the last slide and the stochastic version, we're assuming random mixing. So in particular, the S and I population are always in contact in one another, so everyone is equally likely to come in contact with each other and is always kind of transmitting in a homogeneous way. And that's one of the examples of assumptions that we'll relax in today's talk. The nice thing about the stochastic model is that given a set of parameters, we are not always going to give rise to the same set of curves describing the population trajectory. So in this case, I just have a simple example of one realization from a set of parameters in the SIR model, the stochastic version. But if I were to rerun this experiment, I would get different looking kinds of outbreaks. So this already reflects how the stochastic version of the model inherently captures some of the uncertainty in how epidemics evolve. And also another example I want to highlight right now related to why we like mechanistic models. These parameters, beta and gamma, come into very interpretable quantities such as the basic reproductive number. So when you hear epidemiologists talk about the basic reproductive number, which is the average number of cases caused by an infectious individual, in our model, we have sort of an explicit relationship between the parameters we seek to estimate and this quantity that's very interpretable and used by practitioners. Now, naturally, as I mentioned, one might be interested in understanding how this transmission occurs through a contact network whose structure will be changing throughout the course of an epidemic. So there's a lot of recent growing interest you could imagine in this setting because we, A, have more technology to gather such data at this resolution. We can have maybe mobile health studies that capture people's movements and contacts over time. But also because, of course, recent outbreaks, such as the COVID pandemic, are marked by changes in individual behavior, distancing, quarantining, all these things that fundamentally affect the contact network behind the outbreak. So when I say these well-mixed previous existing works, sort of what a lot of the literature is focused on anyway, a complete contact network is kind of described by this figure on the left. If we had 5 people in a population infected by an epidemic, they're always connected to one another. They're all neighbors in this graph, whereas we might want things like on the right that are a little more sparse that can also change. So these edges, who's connected with whom, is changing over time. Great. And our motivating example today, we'll talk a little bit about one particular case study analysis, is motivated by a study called XFlu. And this was carried out on a college campus where we collected social contacts of over 100 students using a Bluetooth app that pings when they're close enough to be considered in close contact, where they would be likely to transmit, and stop pinging otherwise. So because this is an experimental setting rather than just observational data, we have control. We have really high resolution in observing this contact network as it changes over time. So in this case, we pretty much continuously monitor how that contact network is changing over the study population. And if we just look at the raw data, which is sort of illustrated in this figure, we see that A, it's certainly not a complete network at all times. And of course, it is changing over time. So it's changing and it's kind of a sparse structure at different times. Great. So at least for now, our goal is to incorporate this kind of thing. But in addition to this and even simpler versions, we want to allow the inference to be exact. So we'd like to, motivated by this data anyway, we'd like to model both how that contact network impacts the disease spread, and it should be at least very intuitive why it would do so, right? Because if you're not in contact with somebody, you can't infect that person or be infected by that person. But second, we'd like to describe also the sort of coevolution, in particular how your current disease status might affect your behaviors in that network, whether you're more likely to come into contact or break contacts once you are infected or once you are recovered. Again, all of this is going to be within a stochastic framework, so we can account for the randomness and in turn account for the uncertainty in our parameter estimates. And we'll focus on a likelihood-based approach, which I'll talk about in a little bit. As you'll see, one of the running themes here, why these problems are challenging statistically, computationally, and mathematically, is because we really have partial observations. Even in this setting where we have pretty complete observation of the contact network, other aspects of the data will be missing. And even more so in observational studies where we're collecting things from surveillance data, et cetera, we always have sort of some missingness in the model that we need to deal with in a rigorous way and account for the effects on the downstream inference. Now, before I build all of these things that I mentioned, I want to motivate why it's even difficult in that simplest model I showed in the first few slides. So when you have the baseline stochastic SIR, even with a complete well-mixed network, it's already quite difficult to infer the parameters, at least in these frameworks I've mentioned, in these exact likelihood-based frameworks, without some kind of additional simplifications or assumptions. So for instance, oftentimes what we see in practice is people will approximate the already simple model with an even simpler model. They'll either make it discrete in time, so we're looking at sort of generations, maybe by days or weeks of the process, by kind of lumping together things in time, Or we might look at approximations for different phases of the process. If you have a small population, one might use a simpler thing called a branching process, and this has been done with a lot of theory to back it up. And also for very large outbreaks, it might be reasonable to approximate your population instead as a continuous number, because it's so large, applying things such as diffusion approximations. But each of these is sort of more relevant for one phase of the outbreak and not the other, whether it's the early or late stage. Similarly, just to make the dynamics simpler, people might assume that the infection rates, et cetera, are locally constant, things like the time series SIR or TSIR model. So there's a lot of these things. It's impossible to survey the whole literature. And similarly, as far as beyond the models, as far as inference methodology, because of some of the challenges we'll see, oftentimes people apply very powerful but very computationally intensive general purpose techniques that I will call simulation-based methods. So these methods, which include sequential Monte Carlo or particle filters and approximate Bayesian computation methods, oftentimes what we do is we simulate a lot of sort of virtual outbreaks, hope that they effectively match our data, and sort of kind of brute force trial and error until the parameters sort of match our data. That's a very cartoonish and rough description of these things, but generally the idea is that you need to simulate entire synthetic outbreaks all the time to learn the parameters, and this is a very difficult thing to pull off in many big data settings. So again, our goal is to kind of bring this back to sort of machinery that statisticians are very comfortable with and are sort of very much supported by many applications and a lot of theory, right? So we want to do something called likelihood-based inference. The likelihood is a very central term that describes how the data support the parameters and support the model. And we want to be able to do this in all these things we said, in the continuous time setting, in the fully stochastic setting, and to accommodate additional relaxations of assumptions such as the dynamic networks. So if you bear with me, we have a couple of technical slides, and hopefully I'll be able to give the exposition here without going into the full detail of all the equations we see on the next few slides. But as we've mentioned, this probabilistic formulation of the SIR model is a special case of a quite nice class of models called continuous time Markov chains. Okay, so for now, in the Markov world, these chains are defined by a rate matrix or generator matrix called Q. And the entries of this matrix Q tell us about the rates between jumping process, the rates that the process jumps between states. So if I have subscripts on the xyth entry in that matrix, then what it tells me is that I'm going to wait an exponential amount of time with rate that entry Q sub xy before jumping from state x to state y. And you can imagine for many complex processes on large state spaces, this is going to be a huge matrix. We may not want to deal with it. But this is sort of the fundamental object that defines the stochastic process. For those of you who are maybe a little more familiar with discrete time processes, this is sort of playing an analogous role as the fundamental object as what's called the transition probability matrix. Okay? But the difference is that these are instantaneous rates. And if we believe that we're waiting an exponential amount of time between events, and moving between state sequence x1, x2, x3 in this notation, then the probability or sort of the likelihood of observing a certain sequence of the data, like x0, x1, all the way to xn, observing that sequence amounts to sort of all of these probabilities independently waiting between these events and taking a product of these probabilities. So under the Markov assumption, these waiting times are exponential. And so if you have a little bit of basic knowledge in statistics, we see that it's a product of exponential densities here. And that should be a very nice object, right? This is something that's okay to deal with. It shouldn't be as hard as what I've sort of described at the beginning of this talk. Okay, so this is all good. In fact, let me just go a little further with this likelihood. So why is this a nice object? If I collect some of the like terms, what it ends up looking like is a product of those jump rates between events, and then collecting them to the number of times each event occurred, times collecting all the waiting times we stayed in each state. So that's kind of the second contribution here. And if I take the log likelihood, you can see that maybe with some simple calculus, I should be able to do some very nice classical statistical inference. So if I have the total number of each type of event I observe, and I have the total time spent in each state, you could imagine just taking the derivative of this and setting it equal to 0 to maximize and find the sort of maximum likelihood estimates of the parameters. So here, the maximum likelihood estimate of any of these exponential rate parameters is just given by a ratio of what these are sufficient statistics of this process. So you just divide the number of that event divided by the total time spent in that state. Okay, so that's easy. And if you want to be Bayesian about it too, without going into too much detail on Bayesian inference, you can set up really nice conjugate relationships, for instance, with gamma priors in this process, and see that your parameters, the posterior of the parameters also follows a gamma distribution that's easy to augment by those sufficient statistics. Okay, so in some sense, this is as easy as it gets in doing inference on a nice model, right? So why do we say that likelihood-based inference is hard for even these simple models? And so that actually comes from something I loosely mentioned, which is the missing data, right? We have a lot of partial observations, which I'm going to try to summarize just by a picture. Okay, so if we're observing data discretely over time, and let's say this x-axis represents, for instance, 1 week passing, and we're only collecting disease counts weekly. So in this example, if we observed 4 new infections, well, we don't know, for instance, whether it looks like the left, whether we started with 2 infectious people and we had 4 infections, but also recoveries, and we ended up at the end of the week with the same infected population, or whether we might have started with more, we see those 4 infections, but only 1 recovery, and end up with 3 more than we started with, right? And in fact, there are infinitely many such plots I could draw that are consistent with having observed 4 new infections. And not only does it affect the end number after this week, but also even these times of where these jumps occur come into that likelihood I just showed you. So the problem here is that there really is an infinite space of such functions here, such paths that are consistent with our observed data, and we want to somehow account for all of their probabilities in a principled way so that we can still evaluate the likelihood of our data. So in statistics language, that's called marginalizing over the missing data, and it ends up being extremely difficult in these processes. You can imagine it's a large space, but we've tried to do some techniques here that allow us to get exact solutions that are just rather delicate and don't really work well in practice for large outbreaks. So I think this is the last slide with a little bit of detail. If I now want to look at the likelihood of the observed data only, of maybe weekly data or daily data or something that is observed discretely, but I believe was generated from a continuous time process, then this is what's called the marginal likelihood of the observed data. So what it ends up looking like is a product of the finite time transition probabilities. I've written the log here. But computing these probabilities does require that difficult marginalization integral that I've talked about. So you need to somehow integrate over all the possible paths, and there's infinitely many of them here with some complicated structure, and that will give you the sort of the probability in mind. If you do have a little bit of expertise with continuous time Markov chains, you actually know that there's a relationship between the probabilities we want here and that infinitesimal rate matrix. But the problem here, as you could imagine, is for these processes with large state spaces, you don't want to compute something like this. This is called taking the matrix exponential. It's typically cubic in the size of the state space, which can be really large. Again, it's not just the number of people in your population. It's the number of different configurations of who is susceptible, who's infected, et cetera, which blows up very, very quickly. And it's cubic in that space. So I hope we're with me here. This was the technical stuff, but even without too much of the details, what I want, the takeaway is that we have a model with a nice likelihood. So that nice likelihood, hopefully we can leverage somehow. But as of now, whenever we have this missing data from the observations that were given, we encounter this really difficult integral, this marginalization problem that's very hard to overcome if we want to work with the likelihood exactly. So you can imagine all these approximations might come from sidestepping this issue via some kind of model relaxations. Okay. So a lot of those direct techniques, like I said, they might be very computationally intensive, and they don't extend easily when we want to relax some of these assumptions. But what we want to do is still be in this framework. So we like these continuous time Markov chain models. They have a lot of nice properties, and they've been used. There's a tradition of modeling with them. We'd like to define a suitable generative model that relaxes some of those assumptions to allow us to take into new data like the contact networks, but also make use of its nice likelihood. And so how we'll do this, how we'll deal with this difficult missing data problem, is taking a Bayesian perspective. It's been around for a long time, so it's really about the execution of this. And what we'll do is something called data augmentation or latent variable Markov chain Monte Carlo. The idea is to explore the possible values of those missing data by sampling. So we'll have a Markov chain explore that latent space, but we'll make sure that we do everything so that this Markov chain is still targeting the correct posterior, in this case, of our parameters of interest. Right? So we want to look at the posterior of the parameters under our observed data. We will now augment the observed data with the missing values and target their joint posterior. So I'll talk about that in the next few slides. Okay. So I kind of assume some familiarity with Bayesian methods here, but the idea is oftentimes when we work on Monte Carlo methods in general, we're trying to convert a difficult direct integral into a sampling problem when the sampling is feasible, all right? So we have some kind of sloppy notation here, but it's meant to only convey the idea at a high level. So I don't want to be too detailed and get bogged down like the last few slides. But as I mentioned, the likelihood of our observed data is a challenging object to get our hands on. It's hard to evaluate, and that's because what it effectively involves is integrating or marginalizing out all of those missing data, those complete paths that could have been consistent with our observed data, right? Now we saw that the complete data likelihood had a nice form. So there's something here that's nice, I put it in blue, but we're integrating that against the measure of all the sort of the probabilities of those missing paths, those continuous paths, right? And I've mentioned that we basically can't compute this directly. We technically can in some cases, but it does not scale well and it does not extend to settings like the model will motivate in this talk. So when it's difficult to compute such an integral, a general purpose idea is, well, rather than looking at the posterior of this, right? So Bayes' rule will try to look at it tries to flip this around and target theta given x. Try to learn about the parameters theta given your observations x. But if this likelihood instead has a nice form, what if we can flip that around and target sort of the posterior distribution of both the missing values and the parameters that we originally cared about given x? Right? To flip that around using Bayes' rule, we get to use this nice likelihood in blue, the one that I sort of made a cartoon on in the previous slides. So if that's possible somehow, right? If we're able to sample but somehow make use of the nice form of the likelihood, then we can target at least something different rather than just the posterior of theta. We can target the posterior of theta and what I'm denoting z. So z are somehow going to represent the missing values, and now I'm sampling jointly over the missing values and my parameter values. If I'm able to do that though, so we're happy. So Bayesians have this nice trick, which is to say that it's very difficult to integrate out z here, right? So I might know the likelihood for x and z, but I can't integrate out z. But if I have a posterior on both z and theta, and now I want it only on theta, so I have maybe two columns. I have z's and thetas, and each row is a draw from my Markov chain Monte Carlo sampler. Once I have that in the posterior, marginalizing is trivial. I can simply ignore one of those columns. I can ignore those latent variables. So if you haven't seen this, you can convince yourself pretty easily. It just comes from the fact that this is sort of the empirical histogram distribution of the data. But sort of data augmentation, or this latent variable sampler, basically takes this hard integral. If you can somehow make a sampler that looks at both the missing data and the parameters, moving that problem into the posterior instead, moving it into ignoring the z's after sampling jointly becomes trivial. Okay, so it might be hard to pull this off, but given theta and z samples, if I just ignore the z's, I have a valid posterior with all the right probabilistic properties for just theta given x. Okay, and that's something you can convince yourself of pretty easily. So this is from the original paper on this is Tanner and Wang, if you want to get a reference. Now I'm ready to talk a little bit about the model that I wanted to motivate here. So our strategy is a joint work with Fan Bu, who was a student in our program, Alison Ayala, who is an epidemiologist who's moved now to Columbia, and my colleague Alex Wolfowski. We're going to use this approach to try to enable this inference I motivated on a model that allows for the coevolution of the disease process and the contact network. And in this case, what we'll see is that we want to derive that nice likelihood, even for a more complicated process, and show how this allows us to execute this strategy that I've only outlined on a high level in the previous slides. Great. So for the model building, you'll see that the network process is actually very simple. So each individual in the population is one of these vertices, and we see that we can represent their contacts in any given current contact network in terms of a matrix, right? So this is pretty standard in networks. If you have 5 people and person 1 is sort of in contact with 2, 3, and 4, then in person 1's row, the first row, there's a 1 in person 2, 3, and 4's column. Right? Similarly, if person 2 is not connected to anybody else, there's zeros for all those other people. And every time you have a snapshot of a contact network, you can correspond into a matrix. to allow the network to change over time, it's very natural to just allow the entries of this matrix to evolve, again, according to, let's say, a Markov process, and have these ones and zeros switch depending on those states of the process. And what we would like, naturally, if we want to somehow couple this with the disease, is we would like maybe those rates of whether these edges are becoming zeros and ones or vice versa. Those rates should probably depend on the disease statuses of the two people it is affecting, right? Of the two people, the two vertices. So in particular, these vertices, if person A has disease status denoted A and person 2 has disease status B, then we should have different rates that depend on those statuses. So let's say person I and J are currently not linked, then there's some coin flip with rate alpha where they connect at that time. And then if these people are currently linked, then there's some rate of breaking that link, which we denote omega. And again, alpha and omega will depend on the disease statuses. Now, given that network structure, if currently you have a snapshot of a network, how does the disease flow over that network? And this should also be very, very intuitive because we're seeking to generalize a simple model, right? We want this to coincide in the complete graph case with the simple SIR model. And in this case, if we have an edge between two individuals, I and J, then we still have that transmission rate being the same as in the complete model, right? We have a rate beta that the transmission of the disease occurs along that edge. Also, there's a competing rate, gamma, the recovery rate of the model, that the infectious person, in this case I, recovers. And if this person recovers, then the network structure is intact, but I is no longer in the infectious compartment. Great. So this is very simple dynamics. This is a starting point for incorporating this. But when we put it together, we can look at what happens in the population and see why it's sort of a natural one-step extension of the simple models, right? You have infection occurring at these rate Bs, betas across edges, recoveries occurring individually at rate gamma, and these link rates that I've just described. So if we kind of lump this together and look at what's happening at the whole population level, then the total amount of infection going on is beta times the number of edges between susceptibles and infected people, right? So this is poor notation, but we call that SI of T. In the complete case, when the contact network is not evolving, but instead is always everyone's connected with everyone, this rate, remember in those very first equations I put on the slides, is beta times S of T times I of T, because the number of edges between susceptible and infectious people is just the product between susceptible and infectious people in the complete case, right? So the notation is poor, but we see how it mirrors the simple case. Recovery is identical in this case, right? People are recovering independently, so it doesn't matter about the graph structure. And then overall, we can collect the number of disconnected or connected pairs to calculate the overall rates of link activation and termination. But again, they kind of sum up nicely and linearly in the total numbers. So there's some bookkeeping in defining these quantities M, which I won't go into, but it's mathematically just as straightforward. Okay. So I hope the model makes sense. You might think it's simple, and indeed it is. There's sort of a delicate balance to remaining tractable for inference and being simple, and then in the end, we'll talk about how we're extending this. Right? But this is how we're going to go on with the exposition. And even in the simple model, you see that the complete data likelihood looks a little scarier, but I promise that it's actually the exact same form in terms of sort of what it fundamentally is as the nice likelihood I tried to motivate at the beginning of this talk, right? This is a complete data likelihood of a continuous time Markov chain. So it should have just as simple properties for inference. But in this case, I simply have way more terms from exponentials. I have terms that corresponded to the disease process, which are in red, and to the network process, which are in blue. But fundamentally, it's a product of rates of an exponential and also dwell times within each state that can be sort of represented in this scary-looking integral, but is really easy to evaluate. So this actually is a very nice, simple form for computation. It just takes a little bit of bookkeeping when writing the computer code. Just as in case any of you are working in familiar spaces on sort of contact networks and disease models, there's a lot of really great work there, and I just wanted to talk about how it differs. So there's a lot of great works, for instance, by Ball and Tom Britton's group that look at preventative rewiring. So you have some process on a graph, but now we have edges kind of moving between people rather than disappearing and being added. And so I would say their goal is to preserve some probabilistic properties so that you can do analysis on things like the asymptotics of these processes. And so it's a different game. The thing that keeps it simple is to preserve things like the degree distribution. For us, what we need is we need a process that these things can happen sort of with enough independence that we can write down a nice likelihood and do inference. So they're simple in different ways, but it is a different model than these kind of rewiring models if you've seen those. And that's also very nice work. But it would be very unclear for me how to pull off this kind of inference in that line of work. And I'm very sparse on references in these slides, but of course there's plenty of references in our papers. Okay, so given that this complete data likelihood is nice, despite how much notation there is, we actually have those same punchlines in terms of how nice inference would be under this model in the complete data case. I can do simple calculus and get closed form expressions for the maximum likelihood estimators of all those parameters involved. Or what we'll end up doing is, in a Bayesian approach, given the complete data, we have very nice conjugate relationships, conjugate priors that allow us to just augment the posteriors with simple sufficient statistics. And just to double check that we derived everything carefully, we ran a simulation study on the complete data case. So what we do here is we just run the epidemic, we simulate an outbreak, and in this case I'm just plotting 4 repeat simulations of the stochastic process. And as we record the current data, the current number of infections, recoveries, and everything else that goes into that likelihood, over time, we're plotting up to that time what the maximum likelihood estimate is for each of these parameters. Of course, we've done for all the parameters, but these 4 here illustrate that over time, empirically, our estimates are consistent, right? And that sort of is in line with the theory on maximum likelihood estimators for these stochastic processes in the completely observed case. We basically see that the black line is the true parameter we use to simulate the data. And as we see the outbreak, we see more and more data, we observe it for longer, our estimates, given by those equations, are converging onto the truth empirically.
Next question?
Yeah. Yeah, okay, so the question, yes, that's a great question. The question is, so we start with some network, we run this process, and right now this inference is about the rates about link changing. So what about the link changing themselves, right? Yes. So first of all, in our case study, it's quite contrived in the sense that it's an experiment. So we actually get to observe fully the sort of contact network data, right, over time. In the simulation too, because it's a simulation study, we are simply running the process forward in time. So at every instance, there's a probability, there's these competing rates, right? There's some beta times something, gamma times something, alpha times something, and whatever rate is sampled first, that is the event that occurs. So we'll continuously have either an infection happening or the network changing by one edge. Right. And so we're running those processes continuously, so we do observe everything, right? This is still the completely observed case. And then from that, we're seeing, given all these changes I observed, when I put that information, which is summarized into this M, into these equations, do these equations get closer and closer to the true alpha that I used to simulate that? Okay. That makes sense? Yeah. And so we do, which is good. And this is still a simplified setting, right? Again, we derived the complete data likelihood, and we checked inference in the complete data case. But our ultimate goal is to make use of the nice form of the complete data likelihood to do inference in the much more challenging partially observed case, right? So that's where we're going. And this is just to check that we did all the math right so far. Okay, great. So again, back to this picture though, we validated the likelihood in our expressions, but we still need a valid way to sort of sample that missing data, right? We're doing data augmentation. Here are all these parameters, what I called theta. We're estimating them properly given z. But now we don't observe z, we observe x, maybe things that are weakly, for instance. And we need to now infer jointly the possible underlying trajectories, denoted 2 of which are denoted here as z, as well as those parameters. And that becomes a lot harder usually. All right, so we want to sample over, in this case, the unknown recovery times. Thankfully, in this case, z is not also all the network events. We observe all the network events because we have a mobile health study. So let's go to the data just to get some concreteness here. We have a spread of a disease influenza on a college campus. And what we have is weekly health status surveys on all the individuals in the study. But we have a high resolution, so more like by the second, contact network information from the Bluetooth app. So we have a continuous monitoring of the network. So in some sense, we could have inferred all the network quantities sort of directly. But what we want to do is just do inference in the joint model and see how we can make use of this complete data joint likelihood when we only have weekly summaries of the recoveries. So the latent variable space in this case will still be quite large. It's all of the unknown recovery times of all the individuals, right? So it's these are real numbers, and we need to sort of have all this. First of all, we need to explore this large latent space, but sort of more subtly, kind of an obvious challenge, we need to do so in a way that respects all the constraints of our model, right? So we can't have, if our mobile data is telling us that, person A is friends with person B, and that was the only contact the day before person B got sick, then we can't, there's sort of forbidden moves in putting recovery time of person A before person B got recovered and vice versa. So we need to somehow respect all the constraints, but hopefully do so in a way that also respects the probabilities so that the sampler works well. I'll talk about that in a little more detail soon. Great. So this is one motivating study, but like I said, nowadays we're having more and more mobile health data during the pandemic, et cetera, and so this methodology should apply broadly beyond this case study we considered here. Now back to data augmented Markov chain Monte Carlo, right? The sort of primitive for how the algorithm will work is that there are two steps. First, we need to, given the observed data, somehow propose or draw from the conditional distribution of those unknown latent variables, right? So Z is the missing data, in our case, unknown recovery times, and we need to somehow propose a reasonable distribution of those Z's given the observed data and given the current parameter settings, right? So we're some probability of R's given the parameters theta and the observed data. Now, given that, step 2 should be nice. The whole reason we set it up this way is that once I have the complete data Z and the current parameters, I can update the parameter values using that nice likelihood, right? So we have something nice for step 2. So step 1 is the sort of the bulk of the challenge, and that's what I want to motivate here, that when you design these approaches, it's really the name of the game is designing either conditional samplers or efficient proposals for this missing data. And so this is something that's been known for a long time, but we've been showing how to do this well for stochastic epidemic models. All right, so step 1, like I said, that's the difficult part. It's kind of known to be difficult for continuous time Markov chains. When you simulate a continuous time Markov chain, like in the study I showed the example of, that's easy. But when you simulate it so that it has to pass through certain fixed points and pin it down, that's much more difficult. Right, so in addition, we have to respect those contact network constraints, like I said. One of the pieces of good news I just want to throw out before showing you how this is done is, even though that network, the contact network is imposing more structure we have to obey and makes things a little more complicated, but it also restricts how many possibilities there are that we have to explore. So in some sense, it's actually reducing the size or the dimension of that latent space over Z. And so it actually helps us kind of get the answer faster in some high-level sense, right? So we get more mechanistic information by specifying more of the model. That lets us maybe even mix better in terms of the MCMC. Okay. And so the really interesting thing in this paper is that, again, this first step, you could either propose reasonable things and decide whether to accept or reject those configurations of the missing data, or even better, you might have been able to, while respecting all the constraints, derive the exact distribution of where those Z's might be, conditional on the model, the current observations, and the parameters. And so that conditional draw, it's also known as a Gibbs sample, that's kind of the gold standard, because then you are obeying the constraints, proposing new values, but also accepting all of the new proposals. And that's exactly what we were able to do here. So this is really the work of the student author, Pham Bu, and it's really nice work. This is an illustration of this. So this is kind of a complicated step, so I won't go into detail in the talk. But the illustration is that, like I said, at some times, you need to make the choice that you can't let somebody recover prematurely if that person should infect their neighbor. If later in time, that neighbor needs to be infected but has no infectious neighbors. And so kind of accounting for all of that, but not in a naive way where, oops, you did it, so now you have to reject that proposal. We can reject things that satisfy we can accept things, that satisfy all the constraints, but also are shown to be a conditional draw from the right probability distribution for step 1, right? So at the end of the day, what this is called is we can do a Gibbs sample for the missing data. And so we don't need to waste time generating proposals that are often rejected, which is really one of the key problems in doing MCMC for stochastic epidemic models. So again, I won't go into the technical details here, but that's kind of one of the main contributions. And it's really exciting to know because we've been building off of this as we relax the model even further. like I said, given step one, if that slide illustrated step one, the hard part, then all of these things are one line in R, right? Again, there's more bookkeeping, there's sort of smaller font than before, but we can now sample or update the parameters extremely easily, given the complete data, right? So the whole idea was to propose Z and then have nice forms for the parameters. All right, so don't look at these equations. The point is they're very nice. Okay, in the interest of time, I'll go through the actual results quite quickly because in some sense, the exciting thing here was to revisit this study and do a rigorous joint inferential procedure on this complicated data. But we didn't take home any huge public health lessons here as it was just a small study on a college campus. But what we saw is that we observed it's actually a larger population than simply the ones we had mobile data on. And I won't go into the details there, but we're able to extend it upon a extend beyond the fixed subpopulation assumption, which was nice. But we observed almost 600 students over 10 weeks, among which we have slightly over 100 that we have the full contact network data on. And so we observe tons of network events, but we generally see low network density. So certainly the complete network assumption is not a good one here. And then what we did was, again, we ran what I just showed to do joint inference and sort of exact inference of the posterior under this model for all of these parameters, the network parameters with these infectious parameters, also in the missing data setting. And in fact, again, I didn't talk about this one. We even inferred an external force of infection here. So I won't go into the details too much here, but these things kind of all made sense epidemiologically and just gave a nice sort of baseline check with what we would expect, right? So the really interesting thing here is that we're able to do this, and we know that this is from the exact model posterior. So when we have estimates, we correspond with sort of confidence intervals, credible intervals in this case, that are calibrated correctly for that model as long as the model is correctly specified. And that's hard to come by in these epidemiological studies. All right, so I won't make you look at the table too closely, but sort of we learned that there's a strong internal force of infection, and transmission was pretty slow with quick recovery, and the contacts were short. Great. So some people have commented that there's sort of a big difference in magnitude here. We haven't normalized these by the sort of number of events, so there's a lot more link termination events, of course, because it's a pretty sparse structure. So in this work, I'm going to talk a little bit about other directions after this, but this is one example of achieving some of the goals I've outlined at the beginning, right? So we wanted to somehow relax the simple SIR models for which inference like this was already difficult in the missing data settings. But we want to relax that to also allow for the contact structure to not only not be complete, but to change over time. And so in doing so, we're allowed to somehow describe the interplay between how the disease status affects the network and how the network at a current time modifies the disease spread. Again, this whole thing was fully stochastic, so we did joint inference on the exact model posterior for the parameters of the network and the epidemic. All right? The network model is quite naive. I mean, you might say that this sounded like maybe it's kind of complex with some bookkeeping, but when you built the model, it's a very simple model still, and I would agree with that. So there's also tons of work for extension. So first of all, in this experimental case, like I said, it can be contrived to assume that the network is completely observed. That should be quite rare. So to impute this network, it could be quite different, quite a different problem. And that's one of the future directions here. We want to build, maybe use more information, kind of some good models of how networks, some realistic real-world networks, and use these things to impute, and maybe also put in some human behavior dynamics. That's vague, but these are kind of current directions. And so there's plenty of room for extension among these simple frameworks, but the nice thing here is we've shown how this Bayesian perspective using data augmentation is very flexible for building in extensions such as this network stuff. I'll also skip kind of quickly over these slides, but this is showing how this kind of foundation is also good for different kinds of missing data. So in our case, we had unknown recovery times with a fixed network. We're using some branching process techniques to design efficient proposals when neither the infection times nor recovery times are known at all. And furthermore, these are going to apply to the non-exponential case. So everything here was so far in the Markov land, where everything is exponential waiting times. Some people take issue with this assumption, and in these extensions, we can relax that to any kind of arbitrary sort of recovery distribution anyway. And these things are working really well and scaling really well. So I just want to show that these are absolutely simplifications in the model that we're already building upon, and there's much more work to do in the future. The nice thing here is that when you use a branching process proposal, even though you don't have an exact draw from the conditional, you don't have a Gibbs step, you end up having a really nice property that lets you propose all of the times of infections sort of at once. So that's kind of why our process is going to scale so well to large data settings. This is, again, too much detail for the slide, but we have this nice mathematical property that allows us to basically put down all the infection times at once. That's what all of this, the punchline of all of this is. So kind of illustrated here, we can jointly generate infection times under that proposal by just sampling from a truncated exponential distribution. And then the nice thing here is, I can have plenty of distributions that are quick to propose from, but we found that this is extremely faithful to the SIR process it approximates. So when we have just a couple of, I forgot the populations, it's 5. So when we have 5 observations to 10 observations in this whole timeline to 50, we see that the curves generated from the proposal process are barely off in the first place, but then as we have more and more frequent observations, it becomes almost indistinguishable from the original process. In some sense, it's good enough to just be a straight direct approximation, but we're still doing sort of Markov chain Monte Carlo to make sure that we're doing the minute adjustments to target, again, the exact model posterior. So we're doing exact inference as long as the model is specified correctly. And you might ask, well, the models are never going to be specified correctly, but it's a very useful baseline as people want to build flexible models to know, what are the sort of exact uncertainty properties under a particular model that has been well studied by mathematicians, let's say. So we were able to run this on large outbreaks like the Ebola data here. Okay. So I'm not going to go into too much details of this future direction. So the closing thoughts here are, when we take a fully stochastic modeling approach on these mechanistic systems, we're retaining a lot of the properties that people liked from the beginning of this long tradition of modeling. So they're interpretable, right? We have these parameters that mean something to epidemiologists, to mathematicians, to mathematical biologists. But in the stochastic case, if we're able to do posterior inference, then we have full uncertainty quantification for all the model parameters. Again, this can be exact. We're targeting the exact posterior as long as the model is specified correctly. And this one I say eventually because I think that these models so far are much too simple, right? Some people in the audience here have done a lot more sophisticated modeling that are more geared toward prediction and things like that. So this is a nice foundation for sort of rigorous inference, but we need to build in a lot more of the moving parts to make these rich enough for reliable forecasting and decision making, right, in a pandemic. The nice thing, the good news, is we've already shown with some recent work since here that the continuous time Markov chain framework is very nicely extensible. It rests on a very nice mathematical foundation so that we can continue pushing in a lot of these directions and sort of retain a lot of the tractable properties that allow us to do inference. Right, so again, I've mentioned some of the open directions already on the network side, but in general, we want to extend this to have multiple strains and compartments. We've already been doing some work on allowing individual level heterogeneity beyond just the context structure. So covariates that might make your own susceptibility vary, et cetera. And also more missingness in the level of unreliable reporting rates throughout a pandemic. This is kind of common. Like we said, we want to work with some network missingness and random graph models. We also have some recent work on allowing that force of infection to be a dynamic, but in a structured enough way that the SIR structure still comes through, kind of automatically performing inference on a heterogeneous parameter, but also doing change point detection. And finally, I want to emphasize that what we've done is complementary to some of those existing approaches I've overviewed at the beginning. There are very flexible simulation-based approaches, such as sequential Markov chain Monte Carlo, that I think are simply very intensive, but have a lot of connections with the kind of methodology here. And it would be very nice to create hybrid methods that kind of tie back into the existing literature that we seek to complement in this work. So I'll leave it at that, right? This is a slide of some of the talented student authors that worked on this. Fanbu was the one who worked on the network project I focused on here. Raphael is a current student at Duke who is working on the extensions on the data augmented setting using the efficient branching process proposals. And Jenny Huang is an undergraduate who's worked already on some very serious research on the change point detection problem for a time-inhomogeneous infection parameter. So I'll leave it at this, and I'm just going to leave you with the a little bit of a bibliography for our work, and therein you can find a better literature review for some of the existing work in these directions. So with that, thank you. Thank you all for being here.